Hello everybody and welcome back. Today we're going to work through the last little bit of your 1.1 section, which was dealing with linear expressions. So if you remember, these linear expressions were dealing with x's that were quite simple. It was x with a single exponent. We maybe had some fractions. We maybe had some integers being multiplied in, decimals being multiplied in, fractions being multiplied in, but for the most part it was one line work that maybe had some numbers that were turning into fractions. Here today we're going to be working with what's called rational expressions. Now you've heard the word rational before, like rational numbers. Rational numbers are numbers that are ratio numbers. They're rational numbers. So when we talk about rational expressions, that's when we're talking about using symbols within fractions. So it's rational meaning fraction, expressions meaning essentially your algebra symbols. So we're talking about fractions made up of algebra symbols. All right, so there are two different problems on this packet. One is actually a typo. We're going to need to skip that one. So if you're following along in the notes, this one up here at the top is going to be a problem that is going to be a little bit harder to deal with than we're ready for. So we're going to ignore this problem, and then we're going to instead go down to where I had tried to correct it, and that's like this problem right here. So let's go ahead and jump into this problem. So this is what's the rational expression. So really what we're trying to do is we're trying to find a way to get rid of some of these denominators. And keep in mind exactly how we did this before when we were working with having numbers on the bottom. We were dealing with expressions that had fractions. We were trying to multiply both sides of the equation by some number that would cause the denominators to cancel away. Well here, if I am trying to divide by x plus 2's and I would like to do the inverse of that operation, that's going to be multiplying by x plus 2. So let's see how that would work. I have 2 minus x divided by x plus 2. I'm just going to copy down the original problem, plus 3. And I'm going to multiply all of that by x plus 2. Now be careful to put parentheses around the x plus 2 to show that we're multiplying by the entire x plus 2, not just the 2 and not just the x. And if we do that to the left-hand side, we're going to do that to the right-hand side to keep everything balanced. So again, the idea being that right now I'm just looking for visuals of things that are upsetting me, and right now having an x plus 2 on the denominator is upsetting for me. If that wasn't there, this problem would be so much easier. So I say when doing math, if you want to have something done, let's do it, and then we'll just suffer the consequences. So now we can multiply everything by x plus 2. We'll multiply the left two terms by x plus 2, and then we'll multiply the things on the right by x plus 2. I think the right might be easier to start with. If I have 4 and I divide it by x plus 2, and then I multiply by x plus 2, we might think those will cancel away, so we'll get left with just 4. That seems good. On the right-hand side, if I have x plus 2 and I multiply it by 2 minus x, and then that 2 minus x is divided by x plus 2 again, I'm doing some multiplication and I'm doing some division that's going to cancel away, so I'm left with 2 minus x. And then I need to make sure that, again, this x plus 2 goes to the second term as well. It multiplies in by that 3. So that'll be plus 3 of these x plus 2 amounts. Wow, that's so much easier now. Okay, we can do a little bit of distribution again to simplify up this 3 and the x plus 2. So this will be 2 minus x plus 3x plus 6 is equal to 4. And then from here, it's just combining of like terms. So we've got 2 plus 6 would be 8. Negative x and a 3x would get us 2x's, and then we would have the 4 left over. I would probably want to get x's all on one side and everything else on the other, so if I'm trying to get rid of this 8, let's balance that out. That would leave me with 2x's being equal to a negative 4, which means that each of those x's would need to be a negative 2. Alright, so that means that we're all done. It actually doesn't mean that we're all done. Keep in mind that if we have time, especially in our notes and on our homework, we are going to want to double check every single answer. And in here, I'm going to recommend you do that as well, because it's going to show us the types of problems where if we don't double check our answer, we might get in some trouble. So let's try double checking our answer. That's going to be 2 minus a negative 2. Again, I'm just starting from the very beginning problem, and I'm putting in negative 2 everywhere I see an x. So it's 2 minus negative 2 divided by, instead of x, let's do negative 2 plus 2. Okay, so let's erase that out. Negative 2 plus 2 plus 3 equals 4 divided by negative 2 plus 2. Okay, great. If we simplify that all up, that would be 2, and then minus a negative 2 would be 4 divided by 0 plus 3 equals 4 divided by 0. Ooh, we have a problem. I can't divide by 0. If I try to check my answer, it says it's not an answer. It says I violated something. Why is that? Where did that come from? I'll show you where it came from. It came from this step right here. When you multiply x plus 2 on the top and you multiply x plus 2 on the left to keep that balanced, what we said when we were working through this was that by multiplying by x plus 2, we were multiplying by the number that canceled away the denominators. And that might sound like it was true, but that's actually not a true statement, because I can't cancel out the denominator if the denominator is 0. So really what we should have put in a little bit of a note here is that I can multiply the top and bottom by the same thing. I can try to cancel out the denominator, and I do cancel out the denominator with this x plus 2, but only when x is not equal to negative 2. Now this might sound a little bit weird, so if you have a question, make sure you stop me, raise your hand in the Blackboard system, and I'll be able to help you out. But the idea being that we were trying to divide and multiply by the same thing and cancel that out to 1, but we forgot that variables can sometimes be 0, or they can at least make their statements into zeros. And that's really where we kind of get caught in the details here. So this is what we're going to call an extraneous solution. So an extraneous solution is one where if we try to treat all of these terms as if they multiplied and canceled out, as if we could do all the algebra techniques that we are aware of, sometimes we're going to get answers that we need to double check to see whether or not they actually work. Or you need to remember that if you don't keep track of the fact that sometimes these variable expressions can be 0, then you're going to get numbers that you think are correct that will actually not be correct. So you have two options. Either try to keep yourself really aware of all of these times when you're using variable expressions, or when you get an answer at the very end, you have to check it if it could cause the denominators in the original problem to be 0. Very weird that that kind of pops up, but this is exactly where we need to be keeping track of the meaning of things. Why is it that the top and bottom cancel away? If we say it's because it's equal to 1, we might get ourselves in trouble when that's not the case.